Before modern programming paradigms, developers had to write line after line of boilerplate code just to establish the baseline starting variables of an object. This manual setup was notoriously fragile. If a developer missed a single step or forgot to define a variable, the software would inherit an undefined state, inevitably triggering unpredictable crashes later in the execution. Java addresses this friction structurally, allowing objects to autonomously initialize themselves the exact millisecond they're created. By automating this initial state configuration, the language removes human error from the equation, freeing developers to focus purely on higher-level system architecture. Instantiating a Java object begins with a specific baseline command, centered entirely around the new keyword. The new operator has one job: carving an empty block within the dynamic heap memory and securing a physical address. But allocating space isn't preparing it for execution. This active memory block remains structurally empty, holding no useful data. To populate that space, the system invokes a constructor, a specialized initialization method called automatically immediately before the new operator completes its sequence. True object creation is a two-part harmony. The new operator secures the physical memory, and the constructor formats that memory so the system can actually use it. If a developer writes a class blueprint but doesn't explicitly define a constructor, the Java compiler intervenes and invisibly injects a default constructor. This default constructor automatically fills the empty memory blocks with fixed baseline values, setting all instance variables to 0. While 0 values work for simple scripts, they are highly restrictive for sophisticated applications. Real-world objects usually require unique, precise starting data to function correctly. To solve this, developers write parameterized constructors. When the object is instantiated, arguments are passed through the creation command, and the constructor routes these distinct values directly into the object's memory. It is important to note that the moment you define any custom constructor, the compiler permanently disables its invisible default constructor. By requiring parameters, these custom constructors enforce strict data integrity from the very first millisecond an object exists. Often, a system architecture requires an exact replica of a complex object that is already active in memory. Instead of passing individual numbers, developers use a copy constructor. This accepts an entire active object as its parameter, extracts the values of its data elements, and maps them precisely into the newly allocated block. We now have 3 different ways to build the same object. The practice of defining multiple distinct constructions within a single class blueprint is known as constructor overloading. The Java compiler handles this complexity intelligently. It reads the specific arguments you provide at instantiation, whether that is nothing, a list of numbers, or an existing object, and dynamically routes the execution to the matching constructor. Overloading establishes flexible, contextual-dependent entry points for creation, ensuring a single class can adapt to various operational needs without rewriting core logic. As classes grow in complexity, developers encounter a structural hazard, naming parameters exactly the same as the class's permanent instance variables. This creates variable shadowing, leading to scope ambiguity. The compiler becomes confused about whether to update the permanent class variable or the temporary local parameter. This infographic outlines Java's routing tool to solve this, the this keyword. It acts as a reference pointing strictly to the current object. Typing this, followed by a dot before a variable, forces the compiler to target the class-level instance, bypassing local parameters entirely. The keyword's routing capability extends further. By using this with parentheses, you can invoke a completely different constructor from within the exact same class. This technique allows for constructor chaining. A simple default constructor can delegate its initialization logic to a more complex parameterized one, eliminating redundant code. Ultimately, this acts as an object's operational self-awareness. It allows the object to navigate its own internal blueprint without external confusion. At the end of the object lifecycle, we face a physical limitation. Dynamic heap memory is strictly finite, meaning inactive objects must eventually be reclaimed. In languages like C++, developers are required to write precise teardown scripts manually, destroying objects using a specific delete operator to free up space. Java takes a different approach. An object becomes eligible for removal the exact moment it loses all active references to the main scope. When those connections snap, the isolated object triggers the garbage collector. Operating autonomously, it sweeps the heap, dissolving unreferenced blocks and returning the space to an available state. By abstracting memory reclamation into a fully autonomous process, Java secures the system against fatal resource exhaustion and memory leaks. The lifecycle of a Java object is a highly regulated progression. Instantiation secures the space via new, constructors automatically format the raw memory, and this provides internal context mapping. When the object's utility concludes, the garbage collector steps in, clearing the space invisibly and autonomously. By encapsulating this entire memory lifecycle, Java allows engineers to focus on complex system logic rather than acting as manual memory janitors.